Good to go. We're good. Okay, beautiful. Okay, so we've actually dabbled in differential equations already. Differential equations in simplistic terms are basically integrals that allow you to find the specific solution to an integral. And so we did indefinite and definite integrals. Remember, definite integrals gave you a numerical value. Indefinite integrals give you a function. But those indefinite integrals always had a plus c on the end of them. Differential equations allow you to go beyond the general term for all the possible solutions and get one particular solution. Okay, so it's not a numerical value. This isn't an area under the curve. It's a function, but it's one of the only functions we get. Okay, and this is commonly seen in slope fields, which is why we did slope fields on Tuesday. Okay. So 2 quick things. We're going to use initial conditions to find a particular solution. That's basically what I said. And you should be able to drive a stick shift car. Anybody?
Yeah.
2? Zoomers, anybody drive a stick shift?
Less and less common.
The only reason I know how to is because my dad has one, so he's like, you're learning or else you're stuck. And I'm like, okay.
That's how I learned too. I was learning to drive, and my mom pulled over and said, "Okay, you drive," and just threw me out of the passenger seat and climbed in and refused to move. Yeah, on a hill, nonetheless. Okay, so this slide we'll skip because it pretty much summarizes what I talked about already. So the thing to remember is that differential equations are not definite integrals. And I want to repeat that for the 3rd time. Definite integrals are the area under the curve. It's a numerical answer, blah, 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 blah. That's all that stuff we did. We're not doing that. We're doing indefinite integrals, but taking it a step further. Remember, the indefinite integral is the infinite number of solutions for all those different graphs, whereas for differential equations, we're going to find a particular solution. For those of you that pursue a math career or something involving heavy math, you will take an entire semester-long course in differential equations in college. I actually kind of like that math class as opposed to a lot of my other ones. Something to look forward to. Okay, so we're going to start with something simple. Here's a differential equation. Y double prime minus y equals 0. And I would like to know, 2 different problems here. I would like to know if the function sine of x satisfies that differential equation. I would also like to know if c times e to the x satisfies that condition. And if you're fairly good at pattern recognition, you can pretty much figure out that there's 2 examples, so one of them will probably work, and one of them probably won't. Okay? So it's a plug and chug. And in order to plug and chug, I need to know the function y. I have that, sine of x. And I have to know the second derivative. So please take the second derivative of the sine of x. I'll wait. Little review there, whether or not it has a minus sign. Paige, what's y prime? Not y double prime, what's y prime?
Cosine x?
Of sine x, yes.
Yeah, cosine x.
Oh, sorry, I didn't hear you. Or I misheard you. Okay, so then what's y double prime?
Negative sine x.
Good. Okay, so now we have all the components to check. I'm wondering, is the opposite of the sine of x, that's y double prime, minus the sine of x, equal to 0? And the answer is no. That's negative 2 sine of x. So this one does not satisfy the differential equation. All right, part B. Please take the derivative and the second derivative of c e to the x. What is c, by the way? It's a constant, correct. It's some number. Or it's any number, depending on how you want to look at it. Yanni, what's the derivative of c e to the x?
I did the product rule. Is that?
You can. It's a lot more work than you need to. Here, think of it this way. Instead of c, suppose I had 2e to the x. What's the derivative of 2e to the x?
Like e to the x. No. I don't know. I can't think of it right now.
Kev?
Just 2e to the x.
So what's the derivative of ce to the x?
C e to the x.
And the second derivative?
Also c to the x.
So therefore, the second derivative minus the function, sure enough, equals 0. So like I said, in traditional math fashion, one works and one doesn't. Okay, that's not really that exciting, but it's a nice introduction to differential equations. Figuring out a derivative and a second derivative and seeing if it works. We're going to get into something that's a little more interesting. Okay, okay, yeah, didn't work. And then I think I got this one there. Yeah, oh, it did work. Okay, great, we knew that. All right, fantastic. All right, this is what we want to do. This is a true differential equation. Okay, we're going to find the function that when I, question?
Sorry, I had a quick question on the last one.
Yeah.
I thought when you took the derivative, you had to drop down to x, so it's like xc, and then e to the x just stays the same?
No, not when you have a number raised to a variable.
Oh,
If you have a variable raised to a number, that's what you do. That's the power rule. But that's an e. Remember, e is a number, so it's a number raised to a variable.
okay, so
And the
just-
derivative of e to the x is itself.
And then the constant just stays the same?
Just sits out in front.
Okay.
Okay. All right, so this would seem like it's something we've done quite a bit. There is some function that when we take the derivative of it, we get 2x cubed minus 3x. That's not a difficult problem. But what we're going to do is, because we're going to make this a true differential equation, things have to change. And so we've used this dy dx quite a bit. We've used the dx quite a bit in integrals, and we haven't really addressed what those things do. In an integral equation, I emphasized how you had to always have that dx there because it designates the variable that you're talking about. The same thing is true here. What does that mean? That means a derivative of the function y with respect to the variable x. If we have dz over dt, the derivative of z with respect to t. When we're doing differential equations, though, we're going to add a new element to it, which doesn't cause any problems if you remember that element. And this seems very vague, but you'll understand in a second. So notice the first thing I did. I multiplied both sides by dx. Or if you prefer, I moved the dx to the other side. Okay, this is called separating the differentials. Those values of dy and dx are called differentials. And you'll see at the top of the slide, it's called solving a separable differential equation. I can't stress enough how important that first step is. Initially, you're thinking, well, we'll just take the integral of both sides, right? The integral of a derivative is the function, and the integral of 2, blah, blah, blah. But we need that differential component to designate what the variable is. You must separate the differentials. Okay. Then, how do I get rid of them? I take the integral of both sides. From this point on, it's easy peasy. We've done this a ton. Okay. Max, what's the antiderivative of dy? Y. Perfect. Okay, good. What's the antiderivative of 2x cubed minus 3x?
1/2 x to the 4th minus 3/2 x squared.
Perfect. Okay. And for those of you that didn't hear him, I'll put it up in a second. But one thing you forgot.
Plus c.
Plus c. Right. Now, technically speaking, we should have a plus c on the left and a plus c on the right. Stand up, sit down, 5, 7, 5. Sorry. But to make things easier, I'm just going to put a c on the x side. Well, how can I do that? I'm going to answer my question with another question. What's c plus c? Think carefully before you answer. What is it?
C
Correct. Okay, is everybody okay with that? I know some of you wanted to say 2c, but remember, c is any number. So in other words, if I was to put a plus c on the y side and a plus c on the x side, I would then just move that c to the other side, and then I would ask, well, what's c minus c? You might be thinking 0, but it's not. It's c. Okay? So we're going to make our lives easier by just saying, when I do the work that Max just did, I'm going to choose to put the plus c on the x side. It'll make things a lot easier. Okay? Well done, Max.
Thanks.
Okay, so that's a general solution. And we've talked about this a lot. There's an infinite number of quartics like that. Depending on what your value of c is, would slide the whole thing up and down. Technically speaking, that is a differential equation because of the separation of the differentials that we did already. However, we're going to take that a step further and get rid of the c. Sometimes. Sometimes we won't. Okay, so is this making sense? Yes? Good. Zoomers, does this make sense? I can't see you. You have to say something.
Yes.
Thank you, Prasant, the voice of the Zoomers. You must separate the differentials. And to emphasize this point, I'm going to show you an AP question in a second. Okay, so for those of you, well, not for those of you, that should look familiar. Where have you seen that before?
Slope field?
Yeah. That was that was, I think, number 3 on the slope fields worksheet yesterday. And I said to you, oh, we don't really know how to solve that. Well, guess what? Now we do. And we know from what we did on the slope fields that we should end up with a circle when everything is said and done. You'll also notice in this problem, there's an initial condition in the top. Y of 1 equals 1. In other words, we're at the point 1, 1. So that's going to allow us, when everything is said and done, to get rid of the c term. Okay, so here we go. Whoops, sorry. I thought I had it up here. First things first, separate the differentials. I want everything with the y and the dy on one side. I want everything with the x and dx on the other side. So to make things easy, I'm going to cross multiply. John, there's no wrong answer here. It's just personal preference. Do you want to leave the minus sign with the x's or put it with the y's?
X.
X's, okay. For those of you at home that didn't hear, I asked John if he wanted to leave the x or the minus sign with the x or the minus sign with the y's. You can do either one, it doesn't matter. Solving separable differential equations. I separated the differentials. I'm good to go. Next step, take the integral of both sides. Actually, you know what? I'm going to get all fancies in my pantsies and do that. Josie, what's the antiderivative of y?
Would it be y squared? No.
Close.
1/2 y squared.
Bingo. No plus c, because like I said, we're going to attach that to the x. And also notice that you're going to take the antiderivative of these expressions with y just like you would with x's. It's not like implicit differentiation where you got to do all this other garbage, because this little y thing tells us that that's the variable. Okay? Now we can do a couple things to clean it up. For instance, I can multiply both sides of the equation by 2. Just to get rid of the fractions. I'm going to leave them there just for giggles. But now we need to solve for c. So there's the first part of my separable differential equation, and that I have the function, well, it's not really a function. I have the equation that will give me that derivative. Use my initial conditions and plug and chug. Put 1 in for x and 1 in for y. 1/2 is equal to negative 1/2 plus c. And so we get c is equal to 1. Okay. which means my final solution would be, well, not my final solution. My next step is going to be this. Here's the last step that we need to do. We need to solve for y because we're looking for the function. Solving the differential equation says when you're done, you have to have your value for y, which initially in this problem, I don't really want to do that because I'm so close to a circle formula like I know I was supposed to have. In other words, if I multiply both sides by 2 and then I move the x squared to the other side, I got that nice pretty x squared plus y squared equals 2 equation of a circle, which is what we would like to see. But that's not necessarily really good math for solving differential equations. So I'm going to finish with this puppy by doing y squared is equal to negative x squared plus 2, and therefore y is equal to the square root of negative x squared plus 2. Anna, what did I just do wrong? This is subtle. I don't know if you'll pick up on this, but I did make a mistake. Anybody else? Zoomers? Roomers? Go.
You have to add the plus or minus.
Beautiful. Again, it's subtle. It's subtle, but it's very important. It's very important to the point that you'll frequently see on AP questions, you can get an entire point for just remember it's the plus or minus. Anytime you take this square root, you have to have a plus or minus in there. Now,
How did it go from 1/2 y squared equals negative 1/2 x squared plus 1, and it's just y squared equals negative x squared plus 2?
great question. I multiply both sides by 2. Okay. Go ahead.
Earlier when you said like you could have gotten rid of the fractions, like where which is like y, what 1/2 y squared equals negative 1/2 x squared plus c. When you do that, would it become 2c?
No, it just become 2. So, and there's 2 things I want to finish with, and that's one of them. So give me 1 second, okay? Now, this is proper math. However, I'm now going to get rid of the plus or minus, and this is so. All right, you know what? I don't want to do that. I'm going to leave that there, but I'm going to give this as my final answer. And this is a very subtle point that the College Board likes to really emphasize. And this is what's going to make the difference between I can grind out this answer or I understand what I'm doing. Okay. So what does this mean? This means, this being this expression, the plus or minus means I understand the math in solving for y. Anytime I take the square root of a variable, I have to include the plus or minus values on that square root. The last step, this final answer, you're asking yourself, well, why did he just make the minus go away? Notice our initial conditions. Our initial conditions mandate that the y value has to be positive. So the plus or minus disappears, and it just becomes plus. So what the College Board likes to do is they like to give an answer here where y is negative, so that your final answer has to be negative. So let's suppose Kev is taking the test. He forgets about the plus or minus and just says that it's this final answer here. He doesn't really understand what he's doing. He just made the same mistake I made. He took the square root of both sides and got the square root of blah, blah, blah. Now, did you do that because you understood exactly what you were doing and realized that the initial conditions are positive? Or did you just screw up? And so what they like to do is throw in the fact that your initial conditions make it negative, so that the person solving the problem has to realize it's plus or minus. Should it be a positive or a negative based on the initial conditions? Okay, does that rant make sense? Okay. Take the square root. When you do that, decide if it's positive or negative by looking at your initial conditions. Okay, so Cameron, back to your question. there are two ways to solve the problem. One would be exactly the way I did it here. The other one would be to plug and chug early to solve for C. Because like you said, if I multiply both sides by 2, all of a sudden C takes on a different value here and causes problems later on. Both are correct. It is conceivable that you could have a different value there if you solve the problem in a different order. It's still good math.
Okay.
Okay? Good. Any other questions before I move on? Yeah.
What would be like an example of an initial condition that would like make you think it's negative? Like I'm just confused how we know that's positive.
Good. So if I said something like y of 1 equals negative 2.
Okay.
Okay. The y value is negative, so therefore the y value
Oh, okay.
has to be negative.
That makes sense.
Okay.
I'm just a little confused how so that's the equation, and then that's just one point, right?
Correct.
So how do we know that, like, you want the whole equation to be negative, just from the 1 point?
Because that 1 point is mandating that for that particular solution, think of the slope field. So the slope field has an infinite number of possible solutions, right? I can choose some in quadrant 1, 2, 3, or 4. So what this is saying is I've got this whole slope field of possible solutions, but I want to guarantee that I'm taking one of the particular solutions that the y value is negative. So in order to make that happen, this has to be a negative value in order for y to be negative. Make
So
sense?
it's like you're picking in which quadrant it is?
Correct.
Like that
Yep.
graph?
So we're looking for something in quadrants 3 or 4 where y is negative.
Okay.
Okay? Anything else? All right, so this is an example, as it says at the top, of a question from the 2006 AP test. And you'll recall yesterday I said when we were doing slope fields, you don't have that many dashes. So in this particular problem, they say, what is there, 2, 4, 6, 7. There are 7 dots there that you need to draw the dashes for. And I'm not going to do this, I'm not going to solve this problem because the next slide has the grading rubric, but I want to show you what one actually looks like. So there's my differential equation, dy dx equals 1 plus y over x, where x can't be 0. You're asked to sketch the slope field, so plug and chug some points. You'll notice that there are no dots on the y-axis, so they kind of give you a hint there that you shouldn't be putting dashes there, because that's where x would be equal to 0, and therefore the derivative is undefined. So you go through and you put your little dashes in there. That's usually an easy slam dunk. No problem. I'm assuming you can all plug and chug and do that. Okay. Then part B, find the particular solution for the differential equation for the initial condition of f of negative 1 being equal to 1, status domain. All right, so this is what the grading rubric looks like. You got your little dashes in there. We'll talk about, we don't really care about where the points come from. What I really wanted to get to, and the reason I threw this up here, is trying to drive home this. Okay. So notice what they did. In step 1 of part B, they separated the differentials. dy's and y's are on one side, dx's and x's are on the other side. Then they took the antiderivatives of both. Okay, and so they're skipping some steps here because it is a grading rubric, and they're assuming that to go from step 1 to step 2, you're taking an antiderivative. And in fact, you're getting 2 points for taking an antiderivative. Okay. Then they did the E2 trick to get to the next step. You'll notice here, constant of integration. You get a point for doing a plus c. I don't know why they used plus k, but they did. Okay. Because that plus k magically becomes a c later on, but that's okay. So you get a full point out of 9 points for writing down a plus k. This next point is by using the initial condition. So going up to the original problem, and I believe it was negative 1, 1 is the point. They plugged in negative 1, 1 and found the values for y. This isn't a square root problem, so what we talked about in the previous problem doesn't come into play. But then, of course, solving for y gets you that 6th point. 9 points. 6 of those 9 points are from doing this part of the problem. And this is what I wanted to really talk about. If you don't separate those differentials, they're not going to read another lick past that. You might have the work done 100%, but if you just do this, what was it? It was 1 plus y over x. If you just do this, and all your work from that point on is correct, it doesn't matter. You're not going to get a single one of those points. Okay, so putting in bright red flashing signs, showing you this example, putting a box around this, again, I can't emphasize how important it is to separate those differentials in these types of problems. And then this one, for some reason this year, they decided to do a domain. Normally when these types of problems pop up, and there's almost one on every year's test, it's usually either 2 and 7 or 3 and 6 for the point breakdown. 2 points for the slope field, and then 7 points for the separable differential equation, or 3 for the slope field and 6 for the separable differential equation. Okay. Depending on the problem that they do. Here's one that involves natural logs. The one that I did on the previous screen involves square roots. They like the square root ones a lot. Okay, questions? Go.
Why did they do natural log of both sides instead of the antiderivative?
They didn't. They did the antiderivative. The antiderivative of 1 over x is a natural log x.
Oh.
The antiderivative of 1 over 1 plus y is the natural log of the absolute value of 1 plus y. Those are the antiderivatives here.
Okay.
What you don't see is then they did this trick to get down to the next step. Because e to the natural log of anything is itself. Okay. We're all done. These are students in a parking lot making a slope field. Isn't that adorable? God, if we didn't have COVID, we could go do that ourselves. Wouldn't that be fun? Darn COVID. Bummer. Okay, let me stop this.